Welcome. In this video lecture, I'm going to talk about one of the supervised machine learning algorithm, which is basically a logistic regression, which is basically a classification based algorithm, which means we can use it whenever we would like to classify. We are going to deal with the classification problem. So what we are going to talk about, first of all, we will see what is the major difference between the linear and logistic regression, what are the type of logistic regression, and then we will try to understand how logistic regression works, and then we will discuss about what is the odd ratio and then how the odd ratio link with the logistic regression. Because based on this one we will try to find out the equation of the logistic regression as well. Okay, and then we will try to estimate the parameters of the logistic regression using the gradient ascent algorithm. Okay, so this is what we are going to cover in this lecture is. So first of all, let's discuss what is a linear regression. As we know that we are using the linear regression when the target variable or the dependent variable in a continuous nature. Okay, so that means we are saying that this is a regression problem. Whereas the logistic regression is used when your target variable is in the classification format. Okay, or the categorical form. Either it could be a binary or a nominal or ordinal form. But in this video, we are mainly covering the binary part when the target variable is the binary form. Okay. So as we know that when we are going to predict the prediction using the linear or the multiple regression based problem, so because we have the response variable in a continuous nature, so we are going to get the prediction of the your target response. Okay, whereas in logistic we get the prediction of the target response, but in terms of not values or numbers, but in terms of the probability. And we also know that the linear regression is a straight line. Okay, this is a straight line, whereas the logistic regression is a S curve. Okay, so now the question is, why not we can use in this particular classification scenario the linear regression. The reason is when we are dealing with the classification, our answer should be lie within 0 and 1, because we have get the probability. So that is based on that probability we are going to decide whether the particular data point is lying on the class A or the class B part. Okay, whereas if we use for this purpose is the linear regression, so this linear regression can cross these points. So how we can bound this line that it should be lie within this range from 0 to 1. Okay, for that we are using a special kind of function, which is basically this S curve function that is known as the sigmoid function, which is look like this one. Okay, so basically with the help of this sigmoid function, we would be able to strict the response or the probability should be lie within the 0 and 1. Okay, and if you can see the sigmoid function, which is 1 over 1 plus e power minus y, where y is basically equal to the regression line. Okay, as you can see in this simple linear regression form. Okay, now if you talk about that the types of the logistics, so we have the logistic regression is a binary type, as we have seen earlier, nominal and the ordinal type. So we use the binary logistic regression if our response variable or target variable having the two categories, okay, such as go, not go, you can say defective, non-defective, and so on. Okay, similarly, we have the nominal scale if we have more than two categories. Okay, for that we use multinomial logistic regression. Okay, but over here we are mainly concerned about the binary logistic regression. Now let's see how this logistic regression works. Okay, suppose we have these m features. Okay, from x1 x2 up to xm features. This is x matrix, and our target variable is the response we would like. Based on these features, we would like to see whether our prediction is that whether that particular data point is lying on class 1 or class 2. Okay, so we are representing with 0 and 1, and this z is basically the multiple linear regression. So I'm writing down the sigmoid function, which is sigma z is equal to 1 over 1 plus e power minus z, which we have already seen, where this z is equal to this multiple linear regression, which is going to force this sigmoid function, or the probabilities must be lying within 0 to 1. Okay, and then we can make you can say a benchmark point. If the probability is above zero point 0.5, it is going to be lie in this class. If it is less than zero point 0.5, it is going to be lie within this class. But right now, let's see what's the relationship between this z value and this sigmoid value, because this sigmoid is a probability. So we know that as the z is going to be increased, mean reaches to infinity, so the answer of this is going to be 1, which means that data point is exactly the probability of that point is exactly equal to 1. Okay, so which means we can clearly classify that one. Okay, whereas the z value is, if it is reaches to the minus infinity, okay, so then we can say that, so that is the probability of that particular data point is going to be the 0. So that's where we are saying the answer of this is going to be lie within this 0 and 1. As I we can also mention based on this one, the probability of 1 is going to be calculated with the help of this sigmoid z, whereas the probability of 0, which means the point is lying in the class of 0, you can say, okay, we can calculate with the help of this one, which is the inverse of this one, because we know that the sum of probability is equal to 1. Okay, now, we can also see the classes instead of in terms of the probability, we can also see in terms of the odd ratio. So that means we can convert the probabilities into the association perspective. So what is the odd ratio? So the odd ratio is basically a statistic that quantify the strength of the association between the two events, okay, which is A and B. So we know that how we can calculate the probabilities. The probabilities, that is the number of times the particular event occurred divided by the total number of events. Okay, and how we are going to calculate the odd ratio, that is going to be the probability divided by the inverse, or you can say the 1 minus the probability of that particular event. Okay, so that is the odd ratio basically. So how we basically interpret it, like we are saying that the odd mean the probability of occurring to the probability of non-conforming mean. If the odd ratio is 5:3, which mean the probability of occurrence of that event is 5 by 8, whereas the probability of non-occurrence of that event is going to be 3 by 8. So based on that, we can easily calculate the odds, as well as we can see the relationship of the odds with the probability as well. So let me show you the example. Okay, so we are saying, let's say we have conducted a survey from the 250 customer from the automobile dealership. The customer was asked if they would be recommend the service department to the friend. Okay, so they got the number out of those 50, 250, 210 said that we are going to recommend your dealership services. Okay, so the probability of recommendation is 0.84, whereas the probability of non-recommendation is going to be 0.16. So what is the odd ratio? That is the probability of recommendation divided by the probability of not recommending that services of the automobile dealership. So which is 5.21, which we can write down 5:1. Okay, so that means 5 to 1, which means out of every six, the five people are going to recommend the services to their friend, whereas the one is not going to recommend their services. Okay, so in generically, how we can interpret it, if the odd ratio is exactly equal to 1, which means the occurrence and non-occurrence is equal to 1, so no effect on the outcome is going to be happen. But if the odd ratio is greater than 1, that means there is a more likely that the particular event is going to be happen. Okay, so that means there is more chances that the customer is going to recommend the services of that dealership. Okay, if we take this particular example, whereas if the odd ratio is less than 1, then in that particular case, that the outcome is there is a less likelihood that the outcome is not going to be happen. Okay, So why we have calculated this odd ratio? Because we are going to calculate a regression line, okay, using this odd ratio as well as the probability. So we know that this is the odd ratio, and we know that the probability in the logistic regression, how we can calculate, that is 1 over 1 plus e power minus z, where z is equal to the multiple linear regression. So if I put this into 1 minus p, okay, if we do the simplification, so we are going to get this one, right? And then after multiplying the ln on the both sides, so this is going to be ln p minus 1, so z is going to be the downside, and then ln e, so this is going to be cancel out, and z is equal to basically this multiple linear regression. So here we can write down another way to write down the logistic regression model. Okay, now in order to estimate the parameters, so which means these are the parameters of this logistic regression. So how we can estimate it? So we already know if y is equal to 1, that is indicating the prediction probability will be of the probability of data point x. Okay. Similarly, y is equal to 0 mean, that mean we can calculate the probability of that one prediction probability with the help of 1 minus p, or you can say 1 minus p of x. So in the logistic regression, we can model our response variable because it is in a binary nature. Okay, so we can model it into the Bernoulli form because the Bernoulli distribution is going to be basically having the outcome such as yes, no, okay, defective, non-defective, when there is only the two outcome is there. So the Bernoulli function is f of x is equal to, you can write down simple py of I 1 minus, which means that is not probability of 1 minus yi, which is basically the inverse of this one. So this is the Bernoulli distribution for single data point. Okay, in order to calculate against the particular data point, if we would like to find out the probability. Okay. Now, if we have n data points, so that means we are multiplying this function for the value of 1, which means we are calculating the probability for the data point 1. Similarly, we are calculating the probability for data point number 2. So this same function is going to be written down over here. That is going to be multiply. Similarly, we are going to multiply up to n times. Okay, so how we can write down in a very concise way? So that is going to be this multiplier function. Then p of xi yi from 1 to p of xi 1 minus I, where I is 1 to n, which is indicating these numbers are multiplying up to n. Okay, so this is known as the likelihood function. So in order to estimate these betas, what I am going to do is we are going to find out the log likelihood function, and we are going to maximize this log likelihood function. Okay, so in order to find out the log likelihood, we are going to take the natural log on the both side. Okay, so we know that if the two terms are multiplying, so we can add it. Okay, so this y is come first, then ln into the probability plus 1 minus yi ln to the probability, and we are going to sum all these probabilities. Okay, because they are multiplying, so we are going to sum it up. Okay, so this ln probability, we can calculate it with the help of this one, because we know that the probability of xi is equal to this one. Okay, if I'm going to take the natural log of 1, okay, we know that in the division it is going to be minus ln 1 plus e power minus z. So ln 1 is going to be 0, so that's why the resulting value is going to be minus ln 1 plus minus z. Similarly, if we are going to apply the natural log ln, so ln e power minus z minus ln, so this is going to be 1 plus e power minus z. So if we going to apply over here, so minus z ln e, and they are cancel out, so we got the minus z minus this one, so that is over here. Okay, so if we put these values in this particular equation, what we are going to get is we are getting this one. Okay, so that is yi minus in terms of this one, we got this one. In place of this one, we got uh, this one, and we got this equation. Okay, now what we are going to do is we are basically simply multiplying these two terms. Okay, so what we are going to get is 1 minus yi into z. Okay, so this minus is become first, then minus 1 minus yi is equal to this part. Okay, now, what we are going to do is we are basically, you can say, taking the 1 minus yi is common. Okay, sorry, we are going to just rearranging it. Okay, so what we are going to rearrange, so this value is as it is. Okay, then we are writing down this term, then we are writing down this term. Over here, we are taking the common value, which is ln into 1 plus e power minus c. We have taken the common this value, and then what we are doing is minus yi minus 1 minus yi, and this term is as it is. Okay, so now we are basically simplifying this term, minus yi minus 1 plus yi minus this one. Okay, and then after the simplification, so we can see that this is going to be cancelled it out. Okay, so now if we are going to multiply by this one, is going to be this one, this is going to be this one. Okay, whereas we can once again rearrange it. So this value we have written down at the first place, minus 1 is going to be common, so z plus ln 1 1 plus power minus c. Now, what we are going to do is we are going to prove that this term is basically equal to ln 1 plus e power z, to just simplify our expression. Okay, so how we can do that? So I would like to prove that this term is basically equal to this one. Okay, so what I am taking is from this term I have taken this particular value. Okay, and I can write down this one is equal to this one. Okay, so how you can write down this part, that is ln 1 plus e power minus z. Okay, so I can write down ln 1 plus, in order to make it positive, 1 over e power z. So if I am going to take the LCM, so ln, this is going to be e power z, because multiplied with 1, this is 1, so I can write down 1 plus e power z over z. Okay, now what we are doing is, if I am going to apply the natural log over here, so ln of the numerator minus ln of the denominator, so this term is going to be as it is, so z is going to be first, ln e is going to cancel it out, so minus z. Okay, now if you can see that if I am going to rearrange it, which means if I am going to put over this side, so we have proved it that this term is basically equal to this term. So that means I can replace this term with this term. Okay. Now, after this simplification, I have just written down. So this is a standard simplified form, because our ultimate goal is to estimate the parameters. So over here, I can apply the gradient ascent algorithm in order to maximize this function to find out the new parameters. So what's the idea of the gradient ascent? That is, in order to find out the new beta, we should be it should be equal to the old beta value plus the alpha value, which is a hyperparameter, and we are going to differentiate with respect to the corresponding beta to this particular function. So that means we need to take the derivative of this particular function. Okay, so once again I have written down this function which we have over here. Okay, and now what I am going to do is I am going to take that first order derivative with respect to beta I. So how we can do it? If you can see that this z is basically a multiple linear regression. Okay, so so let me write down yi z means, that is beta naught plus beta 1 x 1 plus beta 2 x 2 up to so on beta k x k. Okay, now regarding this expression, if I'm going to take the derivative with respect to the beta 1, okay, with respect to beta 1, so what I'm going to get is yi, okay, and then this term, out of this term, this is going to be 0, this is going to be 0, these all terms are going to be 0, and because I am taking the derivative with respect to beta 1, so I will get x1, okay. So that means yi x1, similarly we will get x2 x3 up to so on. So that means in general we can write down that either I'm going to take the derivative with respect to beta 1, beta 2, beta 3, that is the corresponding input column, or the variable is over there, so that is x1, x2 or x3. So that's why in generic I can written down this part, okay, this way. Now what I am going to do is I am going to take the derivative of this term. So the derivation of ln is 1 over 1 plus this function. So if I am going to take the derivative of this one, 1 is going to be 0, and e power z. So we know that the derivative of e power z is going to be repeated it up, okay, as the value is going to be the same, e power z. And then once again, if we are going to take the derivative of this z with respect to beta 1, beta 2 up to so on, we are going to get the xi, which means the corresponding to that particular beta, we are going to get that particular variable. Okay, so now if we are going to simplify this one, so so we have just written down this part, okay, and just I am going to just rewriting this term, and now you can see that basically this is equal to the probability. Okay, how it is equal to the probability, that means this one, as we have seen in the sigmoid function, that is basically 1 over 1 plus e power minus z. So basically this element is equal to this one as well. So basically we are saying that we can write down the sigmoid function this way as well, as I mentioned earlier. So let me show you again how we can write down this one. So if you see 1 over 1 plus 1 over e power z, so in terms of positive, because this was the negative. So if I am saying that take the derivative LCM, so this is going to be e power z plus 1 over e power z. So this is going to be inverse. So inverse is mean e power z plus 1. Okay, so this is also the probability. So that means this is the sigmoid function, or you can say the probability pi xi. Now we are going to rewrite it. Okay, if I'm going to take the xi common, so the derivation with respect to beta I, the function is summation yi minus pi xi. So this is basically the gradient from beta 1 up to beta k. Okay, whereas with respect to beta naught, if you can see that these are going to be 0, only we have the beta, so there is no x term, only we have this terminology. Okay, so this is the derivative with respect to beta naught. This is the derivative gradient with respect to beta I. Okay, now we got these derivatives. Okay, now we can find out this new beta. So for that, I have taken a very simple example. If we have these four data points, okay, so we have only one input feature, which is 1 up to 4. We have y is equal to 0, 0, 1, 1. The initialization values, I have taken the alpha, which is equal to this alpha, okay, which is basically zero point 0.1, okay, and I have taken the initial parameter value beta naught, beta 1 is 0, 0. Okay, so in the first iteration, first what I am going to calculate is the z, because we have only one input feature. So the z is going to be beta naught, which is 0, plus beta 1, which is 0, into the x. Okay, so against that, we have basically calculated the z. Obviously, this is going to be 0. So what would be the probability? Obviously, the probability, we are going to put this 0 into the function. So what we are going to get the probability, that is going to be 0.5, because 1 over 1 plus e power minus 0. Okay, if you solve it, you will get the probability is equal to 0.5. Okay, as I have written down over here as well. Okay, okay, now what we are going to do is in step 3 we are going to calculate the beta 1. Okay, so basically gradient of beta 1. So this is xy. These are the probability which we have calculated over here. Okay, so the gradient of beta I was here, which we have proven over here. Okay, so in order to do that, how we can calculate this gradient? That is going to be y minus pi. So that means 0 minus zero point 0.5, 0 minus zero point 0.5, okay, 1 minus zero point 0.5. So these are the y minus probability. Okay, then we are going to multiply with xi. So this column is going to be multiplied with this one. Okay, and if we are going to sum this one, this is going to be the gradient with respect to beta I. Okay, now we are going to use this one in order to calculate the new beta 1. Okay, similarly, I am calculating the gradient of beta naught. For that, we have only y minus pi. So this is y minus pi, and we sum it up, it is 0. So the new beta naught is going to be would be equal to the old beta, which is old beta naught was 0 plus 0.15, okay, plus 1.5 multiplied by the gradient with respect to beta naught, which is 0, so we will get 0. Whereas the new beta 1 is going to be the old beta 1, which is 0, plus alpha, which is 0.5, zero point 0.01, zero point 0.1, multiplied by the new beta, the gradient of this beta, which was 2. So zero point 0.1 multiplied by 2 plus 0 is going to be zero point 0.2. Okay. So after the first iteration of the gradient ascent, we get the new beta naught and beta 1. Now our linear regression equation going to be z is equal to 0 plus zero point 0.2 x. Okay. Now based on that, we have calculated the z values. So against every z value, I have calculated the probability after putting into this particular formula. Okay. Okay, now once we have calculated the probability, I can once again, in order to calculate the new beta 1 value, so I am calculating the gradient value, which is y minus pi, and then 1 y minus p into x. So this is the gradient of beta 1. Similarly, we are calculating the gradient of beta naught, which is going to be this one. So once again, the new beta naught would be equal to the old beta, which is 0, 0 plus alpha, which is zero point 0.1, zero point 0.1 multiplied by this one. Okay, so we will get this value, which is the new beta naught. Similarly, in order to calculate the new beta 1, which is going to be old beta, which is zero point 0.2 plus zero point 0.1 multiplied by gradient of beta 1, which is 0.55. So if we sum it up, we are getting 0.2556. So this is the updated version of the beta. Okay. Okay, so if we see that we will keep going up until either the gradient is going to be 0, or either the difference between the new beta and the old beta is quite tiny or quite small. So we can stop this algorithm and we can finalize these parameters. So I hope you got the idea how we can going to estimate the parameters of these logistic regressions parameters. So thank you so much. See you in the next video.